seat. Please have your seat. Non c'è problema. Thank you so much. As you likely know, Nicola Vittorio cannot be here, but we can have him on the screen, as you can see, and I leave him the stage to introduce this conference. Nicola, please, anytime you want to start.
Thank you very much, Delle. I hope you can hear me. And
yeah, we copy
I wanted
perfectly.
to say good afternoon to everyone. Unfortunately, and with regret, I must confess you, I was unable to join you in Turin. Of course, I'm very sorry about this, but that's life. In any case, I still wanted to welcome you all to the meeting and to say a few words about it. I proposed to Joe and Paolo to organize this meeting during a pleasant aperitif, I must say, in Piazza dell'Unità d'Italia in Trieste in September 2023. The idea was to remember and celebrate the very early days of CMB research, to remember and celebrate the incredible improvements made since then, but also to discuss the current status and the perspective in this field of research. We shared this idea with other friends and colleagues, receiving very positive feedback. I'm particularly indebted to the member of the organizing scientific committee, in addition to Joe and Paolo, of course. I'm indebted to Antonio Diaferio, Fiorenza Donato, and Enrico Predazzi, who are members of the Academy, to Carlo Bacigalupi and Marco Bersanelli, as well as to Nabila Aganim, Eleonora Di Valentino, Enrique Martinez Gonzalez, and Douglas Scott. We wanted to have a very interactive discussions, and for this reason, we structured the meeting in panels, followed by time slot for discussion with the audience. Essentially, for this reason, we asked the chairs to have a proactive role in organizing them. And even if the program is quite full, we think that it will help to give an update and critical view of the subject matter. As a member of this academy, I felt it was my duty to propose Turin as the venue for the meeting. I hope you appreciate and enjoy the magnificent Sala dei Mappamondi, where you are. I propose hosting the meeting to the former president of the Accademia, Professor Massimo Mori, and then to the current president, Professor Marco Mezzalama. I must thank both of them and the whole Academy for the enthusiasm with which the idea was welcomed. I also to acknowledge the financial support from the Academia, as well as the financial support from the University of Rome Tor Vergata, University of Ferrara, University of Turin, from SISTA in Trieste, from the National Institute for Nuclear Physics and from the Planetarium of Turin. The Academy has an ancient and interesting history. Today it is represented by the director of the class of physical science, Professor Daniele Castelli, that will present the Accademia of Science of Turin, and to whom I gladly give the floor. Daniele, please.
Thank you, Nicola. First of all, I'm very sorry that you cannot be here with us. And second, on behalf of the president, past president, and all the staff of the Academy of Science, I warmly welcome you here in Torino. I would like to spend just a few words to introduce you to the Academy. And let me start with this picture, which is not perhaps the best picture to show the palace of the Academy, but is interesting because there is a connection with somehow the topic of this conference. You can see on the background to the right, top right, a square tower, which was the astronomic observatory of the Academy, starting from, I guess, the last decade of the 18th century. Nowadays, there is no more, of course, an astronomic tower, also because the tower was destroyed during the Second World War. The Academy consists of approximately 400 members, divided in different categories, including, of course, foreign members. And we have two classes, the physical, mathematical, and natural sciences class, and the moral, historical, and philological sciences class. There is plenty of information on the website of the Academy if you want to go into some details about the role of the two classes when they were established. Actually, the Academy started with just one single class, and the second class was established at the beginning of the 19th century. And members include a number of outstanding scientists and personality through time, as you can see from a very short list which I put here on this slide. Actually, the Academy beginning with a private society. The three personalities which are just behind me, Gianfrancesco Cigna, Joseph Louis Lagrange, or Lagranja as it was at that time, as he was born in Turin, and the Count Giuseppe Angelo Saluzzo established a private society to support research and experimentation in various fields of science in the broader sense of the word. They were doing some very outstanding work since the very beginning, as in 1759, as you can see, they started to print a scientific journal, the Miscellanea Filosofico-Matematica, that you can see listed here, that today is known as the Memorie della Accademia delle Scienze, which is published yearly. Just to give you an idea, these were two papers by two communication or two reports, as you want to call them, by Lagrange, just at the very beginning in the first volume, one dealing with the method of maximum and minimum, and the other one dealing with, as you can see, the nature and propagation of sound. The private society was officially recognized as the Royal Academy of Science a few years later. In 1783, Vittorio Medeo III di Savoia, King of Sardinia at that time, gave the title of Reale Accademia delle Scienze to the private society. And just 1 year later, the king gave the southern wing of this palace, where we are now, that was formerly a college for the children of nobility. Not the whole palace, but a wing, the one which is, let's say, the one that we saw in the picture in the first one. It is exactly this corner here, and here is the main entrance where you joined the conference. And this room, this hall, actually was the former college theater. It was decorated by Giovannino Gagliari a little bit later, not many years later, by the way. And if you check on the ceiling, you will see a number of figures. In particular, in the corner, there are a number of figures which illustrate instruments of physics, chemistry, mechanics, mathematics, natural sciences, geography, astronomy. If you want to learn a bit more about that, you will have the possibility to do it by checking the website of the Academy, or a short paper that is available even in English, and we will be glad to share with you. On the back side, just behind you, you have on top of the door, of the main door of the hall, you have the motto of the Academy, which is here on the top left. The Academy, since the beginning, had this motto, Veritas and Utilitas. So the truth, which is represented to the left by a woman that is leaning on a globe, and Utilitas, utility, which is characterized by cornucopia and the caduceus, the staff with the two snakes. And of course, this theater changed its function and name when a little bit later, these two globes that you have in front of you, one representing the Earth and the other one the Volta Celeste, were donated by the abbot of Caluso, Tommaso Valperga di Caluso, in 1799, and these are two very precious globes that were made by the very famous Venetian cartographer Vincenzo Coronelli. Around us, a part of the library, and the library was founded right at the end of the 17th century, include a large and excellent collection of historic works in science and humanities as well. You can see a few numbers which are significant for giving you an idea of the amount of the library, the patrimony of the library, as well as we have an outstanding historic archive with some 100,000 letters, codices, almost 5,000 manuscript documents dealing with history of science, drawings of industrial patents, maps, which are stored in different rooms, including this hall, and in some other part of the building. The activities of the Academy since the beginning were quite traditional, let me say. the library, keeping on the archive, publication, seminars, conferences, or conference cycles, which, of course, nowadays include a number of other, let's say, items or events. For example, temporary exhibitions are routinely organized. We started a few years ago already digitization and online publication of most of the library and archives. And of course, we developed a website. We are on social media. We started a few years ago with podcast and videos as well. We contribute to Wikipedia. We have training programs for undergraduate teacher or programs directly for student. This is the homepage of the English version of the website. And by the way, you can see that this international conference is posted on the main page. And I think that this occasion for the 60th anniversary of the CMB perfectly matches with the motto that we can see here, where science makes history. So thanks a lot for joining this conference, and we hope you will enjoy not only our Accademia, but also the city of Turin during these 3 days. Of course, a part of the scientific content of the conference that I'm pretty sure will be quite successful. Thanks a lot for being here. Nicola.
Thanks, Daniele. Thank you for your presentation. Very few words to introduce panel one. Panel one was thought to deal with the very early CMB research. We may say the CMB research of the second half of the last century, but sounds a bit awful said in this way, from both the theoretical and the experimental point of view. So I'm sure that will be interesting, an interesting one, especially for the younger people and for the memories of the protagonists of that period. I was supposed to chair the panel, but given the situation and the difficulty to maintain an interactive remote connection, I have to unplug, and I asked Joe to chair the panel for me. From my side, with Daniele and on behalf of the Accademia, I want to send my best wishes for an enjoyable and successful meeting. And I'm gladly giving the floor to Joe to start with panel one. Thanks a lot. Joe, please.
Okay, so good afternoon, everybody. I really send, for all of us, I think, our warmest regards to Nicola and hope that he gets back to normal very, very soon. It's a great shame he can't be here for this meeting, that he played a principal role in organizing. So I am going to chair the first panel, and it's a great pleasure to begin with reviews of the experimental and theoretical beginnings of research on fluctuations in the microwave background, and Bruce Partridge will give the first talk. And so you have 15 minutes, Bruce.
May I stand here? Or should I sit there? While they're finding the microphone, I have to say it's a great joy to be back in Italy and to see so many friends, including Nicola. I've been asked to talk about the earliest things of CMB studies. Okay. Can you hear me in the back? That's a mess. Okay.
It's for streaming.
Is this better?
Yeah.
Okay. Been asked to talk about the very earliest days in CMB science. These are the years that shaped my own particular path in science. And I have two goals today. The first is to remind us all, particularly the younger people, that the CMB, for the first time, established that the universe really did have a history, and a scientifically viable history. Now, to change. Okay. All right. No. Okay. And again, it's not just a history, it's a scientifically verifiable history. Before the CMB, there was very little attention to either physics or evolution in cosmology. Cosmology consisted mostly of mathematical models. The second theme of the talk is to deal a little bit with the legacy of the very early experiments, things we learned in the early days that bear on later experiments. The $10,000 experiments have a legacy for the $100 million experiments later. So let me begin by summarizing very briefly, since I don't have much time, what cosmology was like in the 1960s, before 1964. It's mostly anecdotal. If you really want the details, see Jim Peebles' magisterial book, Cosmology's Century. But the quote from Willie Fowler sums up the feeling about cosmology well. The big debate, the big issue in cosmology, let's say in 1960, 64, was whether the steady state model or the Big Bang model was correct. Notice the use of the word model. The text I learned cosmology from in 1961 again emphasized models, even philosophy. I find it interesting that more pages were devoted to Mach's principle than to observations. At that time, the sole and rather crucial experimental or observational result was that the universe was expanding, and astronomical observations were focused simply and solely on two questions. How fast was the expansion, and is it slowing down through gravity? These two numbers were the ones referred to by Alan Sandage when he talked about cosmology, a search for two numbers. In these years, only George Gamow and his colleagues were thinking about the physics of cosmology, the physics of a different period in cosmology, the very early universe. And notice, please, the link between physics and evolution. But those ideas were mostly forgotten or ignored. I would also argue, as Jim Peebles does, that while cosmology was considered more a branch of mathematics than physics, the same was true for general relativity. The thought of experimentally testing general relativity was a novelty. And I want particularly to mention two exceptional situations to this general conclusion. The first you'll hear about in just a few minutes from Rashid Sunyaev, the beautiful work being done by the group under Boris Yakovich Sildovich. And the other was the group at Princeton, led by Bob Dickey and John Wheeler. I've listed here some of the issues that were floating around in the late 50s and early 60s in the so-called gravity group at Princeton. They were interested in experimental tests, not only of general relativity, but its underlying assumptions, and also interested in physical cosmology. I won't have time to talk about any of these. If you are interested, catch me during coffee. The one exception is Dickey's notion that the universe may be cyclic. Expansion followed by contraction, a bounce, unexplained, expansion followed by contraction. In each such cycle, stars produce heavy elements, and to maintain the cycle, you have to get rid of the heavy elements, and that's done, in Dickey's view, by having a hot end to each cycle, and therefore a hot beginning. A hot Big Bang of our particular cycle. Okay? If that's true, there are some consequences, and we'll come to the consequences in just a moment. But I want to make the point that the Princeton group was well poised to supply an explanation for a discovery by Penzias and Wilson. We all know now it was the cosmic microwave background, but in 1964, it was not the cosmic microwave background, it was excess antenna temperature. It needed an interpretation, and the Princeton group supplied it. Here's a figure from the little paper by the Princeton group, Dickey, Peebles, Roll, and Wilkinson, essentially plotting a history of the universe in terms of its density and temperature. Okay. Now, if, in fact, the microwave background is cosmological, so that the C goes with the MB, then there are consequences, and we'll come to those. But the question is, was the microwave background truly cosmological? And I want to emphasize that at the time, we recognized that there were a series of tests of this hypothesis. The first has to do with the spectrum. If you imagine a hot initial moment in the history of the universe, any radiation present, now downshifted to microwave, that radiation would have a black body spectrum. Material would be thermalized. So the spectrum is the first test. And the second was isotropy. That is, the microwave background should be essentially isotropic, not concentrated along the plane of the galaxy or the ecliptic or anything else. Those were the two major tests. There were two minor ones as well. The first is the dipole moment. We knew in the early 60s that the Earth was in motion. That should induce a dipole moment in the microwave background. That's another test that the background is cosmic and not local. And also the fine scale isotropy. That is the radiation made up of little dots, which might be true if the radiation is coming from discrete sources or not. Okay. All right. And it was those tests that lay behind many of the early observations. I'm not going to talk about this because I don't have time, but I do just want to mention that Dickey was famous for null experiments. Again, you can ask me about some of them during coffee. But in some ways, tests of the microwave background's cosmic origin also turned out to be null tests. Is it isotropic? Yes or no. Is it black body? Yes or no. Okay. So let's turn first to the spectrum. As I suspect you all know, the Dickey group was already at work building equipment to detect a cosmic microwave background when Penzias and Wilson made their announcement. Okay. This experiment was led by Peter Roll and Dave Wilkinson. Okay. Here's a sketch of the apparatus. I want to make a couple of points. One is that there was a switch between the sky horn, which received the microwave background, and a cold load. That turns out to have been a bad idea because the switch was not necessarily symmetric, one of the lessons learned in the early days. But here is the result. Because their experiment, the Roll and Wilkins experiment, was at a different wavelength from the discovery by Penzias and Wilson, you can plot a spectrum, and it's shown here. To me, this is one of the most audacious and also prescient graphs in all of astronomy. 2 points through which they drew a black body curve. Okay. Was it really the case? There were some other experiments that produced results, but most of them were either at low frequency or were not very precise. So, for instance, it was difficult to discern the difference between a 3 Kelvin black body and a much higher temperature gray body with a Rayleigh-Jean spectrum. And it did not help that the rocket observations that were available by the mid to late 1960s were in better agreement with a gray body spectrum than black body. So the test had not been definitively passed that the CMB has a thermal spectrum. So Dave Wilkinson and I and a bunch of other people set out to make measurements that were both more precise and more consistent. The idea was to make measurements of the spectrum of the microwave background at a series of different wavelengths with essentially identical equipment, same design of equipment, with very careful attention to systematic problems, the emission from the Earth's atmosphere, pickup from side lobes, and so on. This shows 3 of the 4 radiometers. We made the observations at a high altitude site in California. And this was the experimental scheme. The equipment actually faced down. Radiation from the sky was reflected off a metallic reflector and into the apparatus. And then we could put in place not the sky, but a calibrator load at liquid helium temperatures, overmoded so we didn't have to worry about emissions from the wall. Attention always to systematics, minimizing them or measuring them as much as possible. And here are the results, plotted again on a black body curve. Consistent measurements at 4 different wavelengths, consistent with a black body curve, and inconsistent at a couple of sigma with a Rayleigh-Jeans curve. So by the time these results were published in 1967-68, test 1 had been passed. The spectrum appeared to be black body. And I should add parenthetically that the rocket experiments gradually converged on a consistent result, even though they had not been consistent initially. Second test, isotropy. Isotropy measurements, Planck, COBE, WMAP, people won't believe this, but measurements of fluctuations are much easier than absolute measurements, right? Calibration doesn't have to be as good, but you do need a reference. And this, the so-called isotropometer at Princeton, was designed to use the sky itself as a reference, a technique that was followed up in COBE. Rather than a rapidly spinning satellite, we had a reflector. First, we looked up at a point along the celestial equator, roughly speaking. Then the reflector came up, and we looked at the north celestial pole, a fixed point on the sky. So we were making sky measurements comparatively. By this simple technique, and by the use of a switch it was symmetrized, we were able to make much more precise measurements, and we were able to show, as this slide shows, that the radiation is isotropic to something like 0.003, 0.005 Kelvin. In other words, a roughly 50 to 100 times improvement over the initial rough estimates of Penzias and Wilson. In addition, there's no clear evidence of the galactic plane in those measurements. Okay. So the second test had been passed. The radiation was black body, and it was isotropic. I'll just mention briefly here the notion that you need a reference. You need some fixed source to compare to. In the case of Planck, that was a cryogenic load. In the case of COBE, it was two different chunks of the sky, and that same principle was applied in WMAP. Okay. But you need some reference. Two minor tests. The first is a dipole. This is a contested area. It's not clear exactly who and exactly when was the first person to determine that the CMB did in fact have a dipole moment. We now know it to high precision, but its discovery, I think it's safe to say, is debated. The one thing that was interesting back in the 60s is that when the dipole was first clearly measured, let's say to 10% accuracy, it was in the wrong direction. We anticipated about 300 kilometers per second of motion in this direction from the rotation of the galaxy. And instead, the dipole was almost exactly in the opposite direction. The only way you can justify or make those two things agree with each other is if the center of the galaxy is in substantial motion compared to the rest frame of the CMB. So we also discovered peculiar motions of the galaxies, in a sense. All right. The second concerns fine-scale isotropy. That is it possible that the entire microwave background, forgetting its spectrum, is made up of the emission of radio sources or some such? And the answer is no. The background is too smooth on a small scale to be explained by sources. So, by the late 1960s, essentially all four tests had been passed. Here's a crude and early way of representing isotropy or anisotropy as a function of angular scale. You'll notice that there was no concept at this time that there was such a thing as a power spectrum. Okay? That came later, and you'll be hearing about that later on. Okay? All we did in the sort of spirit of null experiments was to plot upper limits as a function of angular scale of the beam. Crude way of doing it, but that's what we were doing in the late 60s. So, by 1969 or so, all these tests have been passed. If you want to go back and read a sort of historical document written at the time by somebody who didn't really know quite what he was doing, see my paper in the American Scientist from 1969. I'll end by saying that in 1968, I made a fateful trip to Russia. Okay? I can remember well being brought into a large dining room / study area at the apartment of Zeldovich with a bunch of bright young Russian scientists and being drained of information and then having information implanted from them. It was a marvelous moment, okay? And I look forward to hearing about the early days from one of the people who was so responsible for them. But I also want to note something else. And that is in the 1970s, after the microwave background had been proved to be cosmic, there was a sort of lull. I think people were interested in this thing, but it wasn't clear what good it was doing, what it was useful for, what its consequences were. So there was a period where the rate of publication was pretty minimal. 10, 20 papers a year, or something like that, compared to the hundreds that now mention the microwave background. and it didn't really take off until a couple of things happened. One is the role of theorists, which we'll be hearing about later on. The theorists told us what we should be looking for and what we should have been looking for. I'm looking at Dick Bond and George Eustathiou and Joe Silk, okay? And the other thing is that we were basically waiting for COBE. We were waiting for an experiment done in space without the problems of atmospheric emission and so many of the other systematics that interfered with the early work. So I'm going to end with this happy slide. Oops, I guess I'm not going to end with this happy slide. Yes, I am. There we are. And thank you very much.
Thank you so much, Bruce. So I think we're going to defer all questions and discussions to the discussion section. And so let me now call on Rashid Sinyaev to make a contribution to the panel discussion.
As official with you, what is possible to speak without jacket? I don't know. Oh, thank you. Yeah.
No, please, not that.
Okay, I will put somewhere. Okay. Excuse me. I wanted to be. Yes. Let us start because, yes, this is third version of my talk because first version I tried during 15 minutes to remember everybody who contributed our science, the CMB cosmology, due from 1965 up to when CMB was discovered, up to COBE launch. And COBE launch was November of 1989. And it is 25 years, an almost a long time. Therefore, I found that I should devote, I should describe every year in 36 seconds. You understand? 25 years during 15 minutes. This was first version. I forgot about all the names. Then I wanted to make more pictures. This was also a disaster. Finally, I decided, okay, what I remember the best, I should speak about this. And immediately I can tell you that I will tell how I started to do theoretical predictions, because this was what Zeldovich requested from me. Do theoretical predictions and then observers. Yes, very soon we'll discover this. I can tell you a lot of predictions of Zeldovich were correct, but these predictions that people who are doing experiments will discover everything within rather soon, in a few years. I can tell you some of our predictions are not solved till now. This is not good, but this is a situation. And I remember one of the theoretical predictions which was made or published in '68. In reality, it was, I heard about it a little earlier. Then paper came from United States because Andrei Drashkevich in the Zeldovich group decided that he came from nuclear program and he knew about different types of viscosity and told that there will be radiative viscosity and it will dump all fluctuations at small scale, at some stages of evolution of the universe. But Andrei was telling us about this and was looking for the better solutions. But then Astrophysical Journal came to us, arrived in '68, and there was everything was written, not as complicated as Andrei was writing, but all physics was there. And this was now, this effect has a name on the sky, and it is observed on the sky now. Just many telescopes, radio telescopes, especially South Pole telescope first made really great picture. This was silk dumping. And it is great because this silk, without dumping, is sitting here and is our chairman. But I can tell you that this was, Andrei never published his paper because everything was written. He was just late. But he included this to his, in German, this habilitation, second thesis, which is necessary in Russia to become professor. It was there. But I can tell you that this discovery was absolutely tremendous, but it also was, everybody believed it, but it was really proved only 40 years later. It was, Joe remembers, I think, every year, but nobody had any doubt that this process works. And when I read this paper, I recognized that it is enormously important to say something which physically is correct and which should occur in the universe on the sky. But when experimental people will find it, it is already a great question. But it is important to say, as Deutsch always was telling me, it's important to publish the ideas. Okay, next slide, please. Is it possible? There is nobody. Next slide, if possible. Or maybe, there is everything. Excuse me. Maybe I can do this myself. Or it's already done. You see on the left, Yakov Zeldovich, and on the right, this is me at the same time. And in March 1965, I was a fifth-year student who, before this moment, studied physics and elementary particle theory. I became a student, diploma student of Yakov Zeldovich. It was a very interesting story because I wanted to be a theoretician, and it was very difficult in the huge institute where I was, working in the, student was working in the lab. But then one young lady who was working with us told me, you are giving and giving exams, and people are telling, please give additional exams, only then we will take you to theory. I will tell you the truth. Nobody of these people who are asking you to give additional examination has position. No positions in theory. But I know now one person who returned to Moscow and looking how to organize a small group of young people who wish to be serious. Go to this person, this is a telephone. And I believe this young lady, she was 5 or 6 years older than I am, and she was very kind to students. And students usually like this when somebody gives them the instruments and so on to work. And I went to this person. He invited me after my call, and it is interesting that he invited me in the day when I turned 22, and after a week, this was very difficult to speak. He was asking different questions in absolutely different directions, and it was necessary to answer, in the worst case, within 1 day. After 7 days, he told me, okay, today is my birthday. He turned 51, therefore I agree to be your advisor, what to cite. Later, I recognized new thing because I didn't know who is this person who was unable to sit. He was jumping, telling something, going, again returning, and all time was exciting. And then people, after several months, explained to me that this is one of the most decorated people in Russia, person who made contribution to the Russian atomic and hydrogen weapon, which he never was proud of. I know all this. And I can tell you also about the girl who sent me to him. After maybe 2 years in his home, I intersected with this young lady, and this was his daughter, Oля. Understand me? It was, and I remember her voice. She told me, go try to speak with him. I think that he would like you. And you know, this was the day when I first time saw Zeldovich, and when Ola told me go, this day changed whole my life. It made me in reality very happy. I will not speak about all what is written here. I can tell you that he gave me in reality 2 copies of his preprint or reprints. One of them was the lectures he gave in Estonia, and one he gave in a closed city in Sarov, where these bombs were created. And he gave me copies, and I was reading them several months, and I was amused how his goal was to show the difference. George Gamow proposed the hot model of the universe. Everything starts with a very high fireball, and Zeldovich himself was advocating the model which is cold, and everything started from the family of the cold, very cold neutrons. And there were different things. Biggest difference was the amount of helium. In the neutron system, helium was practically absent, primordial helium, and here all computations of that time were giving not even 28–30% of helium, which very rapidly was recognized that it's much more than on the sun. Therefore, the situation was not simple. And I came to Zeldovich in March '65, but in June '65, great news about the discovery of rather bright radiation coming from, according to the first paper, also from practically from all directions. It came, and there was enormous noise in Moscow. And Zeldovich organized and invited a lot of people to the all Moscow astrophysical seminar at Moscow University, and there in the room at that day, people were staying everywhere, and he was telling how important this discovery. And reading his lectures and then hearing his talk, I was amused how much people in reality knew about processes in the early universe. And this was connected with electron-positron pairs. Hayashi was writing this in 1950. A lot of physics was coming, and theorists were trying to apply this to the universe if it is hot. Therefore, it was enormously interesting. And I'm glad, because I also considered, for me, this was very important when he was speaking about dipole anisotropy, because we are moving, you told about around sun, but I already knew at the time that we are moving also around the center of the galaxy, which is order of magnitude higher velocity, and therefore dipole is much bigger. It was very interesting to hear all these things, and also a lot of people at the time around Zeldovich were a lot of people who were doing general relativity. They were all, Novikov and Drashkevich, they all were interested in anisotropic universes, which can create, anisotropy of, very strong anisotropy of microwave.
Closer to that thing.
Oh, to the thing.
Yeah, stay closer.
Okay, thank you. Yes, and people were speaking about this anisotropy, and Zeldovich was not interested that I will join this crowd of people who were doing general relativity. He was asking me in the first days of our meeting, what lectures you like? Do you like any lectures from people who are doing experiments. And I told, yes, these were beautiful lectures, because it is unbelievable how, for example, this, bubble chamber, or, you understand, there are many, many instruments which is very difficult to even to explain how much physics is working in each of these instruments. And I told him I like this, and I like all the methods of detection of the particles. Then he told me, okay, you will be working in this direction. Again, I am very happy now, because there is no anisotropic universe, but all these physical processes are working in the universe. Yes, I can tell you at that time, a lot of people were working on helium, how important and so on. And there were very many people. The best work was done by Fermi, Enrico Fermi, and Turkevich. It was not, they never published it. It was done also in the, when cross-section, for example, cross-section of deuterium plus tritium was enormously big secret. And Fermi knew it, and he gave value to Turkevich, and Turkevich computed, and immediately amount of helium became lower. It was 30%, and they found something 24, 26. And Zeldovich did the same. Smirnov told me that he computed also with secret Russian cross-sections. He also, there is paper, I think it was published in '64 in astronomical journal in Russia. Practically nobody is quoting it, but it was one of the first papers really done on good level. But everything, discussions finished when Bob Wagoner and Hoyle and Fowler wrote the paper, and everything was done. You are changing entropy, and you are getting abundance of every elements immediately from their computations. It was '67, I think.
Rashid,
it was great time.
Rashid,
and
5 minutes.
oh, I thought that you will permit me the same time as my friend. Okay, and yes, then I will go ahead. Let us do thing which is very important. A lot of people were writing that if our universe was hot, then there would be, how to say this, there would be the moment when all hydrogen in the universe during expansion will become neutral. And there should be recombination. Nobody was using what and how it works. And in '66, let us do following. In '66, yes, Zeldovich asked me to tell to everybody how recombination is going. And very simple, there is well-known formula of Saha, made in Dhaka, Bangladesh now, where he found what is the ionization equilibrium of any element inside stars. I did the same and showed that this process is going very fast. Look to this curve. This is curve, which is according to Saha formula. This is Saha formula, and this is the very rapid recombination, and everything is occurring around 1,000, redshift 1,300. After I finished, my friend, at that time we were working together, Vladimir Kurt, who was measuring brightness of Lyman alpha line, how to say, reflected on the hydrogen by hydrogen atoms from sun, just reflection. And he asked me, he was working only with Lyman alpha, and he asked, and where is my Lyman alpha line? I told him, oh, Lyman alpha line is in the part of CMB where H nu divided to KTE is equal to 30, E minus 30, it's negligible, it's not important and doesn't influence. Kurt told, okay, but I was unable to sleep because the same night I computed what is the cross-section for Lyman alpha line, you know, for life, and this cross-section was absolutely huge, and it was obvious that this line cannot go due to Hubble expansion to the wings. It's a very slow process. And then I discovered a paper of Kipper from Estonia, who in 1940 wrote the paper about 2s, decay of the 2s level. Transition in a hydrogen atom, 2p1s transition is permitted, and lifetime of 2p level is 10 to the power minus 8 or 10 to the power minus 9 seconds. And 2s is 2-photon decay, and its life is 1/8 of a second, 7 orders of magnitude longer. And if we will put this entire lifetime of the 2s level, you will find, you will find completely different curve. And this is this line, solid, you see. And it is very important because I found at that time that scattering, real, how to say, Thomson scattering of the radiation might occur only at redshifts much smaller than in the standard electron fraction Saha formula. And you can see there are several other predictions. Victor Dobrovich made great idea. He told that transition between high levels of hydrogen, they should also give a lot of lines, and we should find them. Then we recomputed this. Jens Hlubo is here, and Jose Alberto Rubino Martin, we computed. Effect was 100 times smaller than in case of in Dobrovich computation, but nevertheless now there is a dream that people will detect it, and it would be possible to go much earlier with these lines. Yes, excuse me. And I can tell you that this is now what we can observe. This is the visibility function. It is the region from which we are getting the signal of CMB fluctuations. You know this. And it is at redshift of the center on the redshift smaller than 1100 here, and it is great that experiments just confirmed this theory. 1 second, I think that I had also, no, I did, yes. This is the visibility function which we computed in 69 and published it in 1970. It is it, and it is shown that the maximum is at redshift between 960 and 1135. It was great, and now WMAP and Planck fully confirming this. I will very rapidly tell you now about the predictions of baryonic acoustic oscillations and acoustic peaks. With Zeldovich, we wrote the paper, which is based in reality on standard sound waves discovered by Lifshitz in his thesis in 1946. Lifshitz showed that in the universe, if in radiation-dominated universe, the perturbations or adiabatic perturbation goes through the horizon, then they form standing waves, and standing waves are going, you see here, frequency is high, lower, but they all are born with the same phase. And in the moment of recombination, they are coming with different phases. Therefore, we are getting this picture, and you know how angular fluctuations spectrum is changing, also has these acoustic peaks. Then in 1966, Zeldovich asked me to review on the seminar the preprint of Laser and Burbage's, who sent us and wrote that CMB is just light from the stars scattered on the dust and, you know, thermalized by dust. And obviously, I made very simple estimate on the seminar, what is the Rosseland free optical depth of the universe for CMB. And it was up to redshift 10 in power 8, close to 10 in power minus 5. It's unbelievable. Normal absorption doesn't work at all in the universe. Then I made estimate for the Thomson optical depth. And optical depth was of the order of 10 power 7 for these things. After that, we started to work with Zeldovich about the change of the radiation spectrum due to scattering on the hot plasma. Everything was done by Companeit's equation, but it's easy to say that normal Doppler effect, Thomson effect plus Doppler effect due to thermal velocities of electrons give you one peak much stronger than another one. And then the whole spectrum is decreasing in relay gene spot and increasing in different things. 1 minute, okay. Yes, this was Y distortions which people are looking for now, and another was another obvious spectrum after energy release in the universe was Bose-Einstein spectrum, which also we did. Okay, there are beautiful theory how to create black body from Bose-Einstein radiation, and result is the following. This is the last slide. I am showing you here the last scattering surface. Excuse me, I became nervous due to because our chairman is so tough. You see here, yes, you see here the last scattering object, last scattering surface at redshift lower than around 1000, and there is also black body photosphere. And black body photosphere, it is a place where any energy release will be fully thermalized. And this region, black body photosphere of the universe, was existing when our universe was only 18 years young. This redshift 2 million, and all giant energy release processes, nuclear reactions, electron-positron annihilation, cannot give any traces which we can detect. But after any energy release, decay of unknown particles and so on, after redshift 2 million, will give us the, yes. And we wrote this in Zeldovich in 1970. 25 years later, the COBE spacecraft went up, and I was very proud where they gave upper limits, not detected, both on wide spectral distortions and Bose-Einstein spectral distortions. And they are on the level of 10 in power minus 5. Now we dream that next generation of experimentalists will be able to find this process. There is, for Y process, it is obvious that that it will be possible, and I will show you only that the same processes are working in the clusters of galaxies, and this is 689 galaxy clusters discovered on 500 degrees by the South Pole Telescope just due to Y distortion, due to this spectral distortion of CMB, because there is hot gas. And I can tell you this gives us immediately that on whole sky there are at least 250,000 clusters of galaxies with hot gas. And this is great. I can tell you that X-ray astronomy, I am working with eROSITA data. We cannot detect on the whole sky 250,000 clusters of galaxies, but CMB can. This is a great difference. Okay, thank you very much. And Joe, thank you very much that you were so polite.
Okay. Thank you for keeping to time, almost, Rashi. Chris Goski, please.
Thank you.
So Chris will give the third panel distribution. Comment. Should be good. As we get this ready, let me just say that when the discussion begins, we will have a surprise unannounced talk on Spherex by Jamie Bock. So that will come in the discussion before we discuss what Chris and
Thank you.
Bruce and Richard have said. Please,
Good
Chris.
afternoon. It's an immense pleasure to be here. Thanks to Nicola, Joe, others for invitation. It's the third time we had 25th in L'Aquila, actually in Italy, 25th anniversary, 50th in Princeton, now is 60. Perhaps the cadence should shorten up, so we continue going with these meetings. I've been asked to step in and say something about COBE. Again, great pleasure to be able to try to do that for you. Of course, discovery was mentioned. Just to mention, this was worth half of the Nobel Prize divided between these two gentlemen. And then, after all the romantic time, heroic time described by Bruce and Rashid, there was a serious time to prepare for a space mission. So this is a brief calendarium of preparation for COBE. Started with 74 proposals to NASA, failing, resurrected in 76 by forming a team that, out of 3 proposals that focused on CMB, was supposed to put together a concept for a mission unifying 3 of them on one platform. In 77, that concept emerged. COBE was originally conceptualized to be launched on the space shuttle, comprised of 3 instruments, FIRAS, DERBY, and DMR. Everything was going well, then the shuttle exploded, then there was a delay, enormous effort on redesigning for rocket launch, 50% of weight reduction, for example, things that are shocking in terms of when you see the time scale over which this was accomplished. And as Rashid said, 18 November, 1989, COBE was launched. I particularly like this piece because it shows a footprint from conference in '79 in Copenhagen, where Ray Wise went with John Mather and Tim Kelso. The other 2 gentlemen presented a longer paper on COBE design. Ray wrote just that, and it's a masterclass on project description in concise form. It actually contains everything we still should bear in mind. Why you would go to space in blue, and importantly, that predicting already then that, or expecting there that one of the more serious problems for interpretation of the results and comfortable derivation of results would be what he referred to as astrophysical noise or foreground emission that one would have to deal with. How important it was to have a complement of 3 instruments working together, helping one another in dealing with this problem. This is the COBE science team early on. Out of all of these people, we just have Chuck today in the room. Dave Wilkinson's on the left. You see young John Mather. Kind of shocking to see how young some of these people were when such a magnificent project was conceived. And then eventually, of course, they got the Nobel Prize. And I won't speak much about FIRAS. This was a worldwide sensational presentation of the result. I'll only mention briefly that Berkeley-Nagoya experiment a little earlier purported that there was very significant spectral distortion to the black body, which has spawned enormous trail of theoretical work trying to explain it. Gush and Halpern in Canada built a rocket experiment that was supposed to measure that and did, but briefly after COBE. So the confirmation of this result was very fast through independent instrument. And remarkable thing about that was, of course, that not this curve, but the first one presented to the community was the result of only a few minutes of observation of just opening COBE to the sky and pointing FIRAS and getting the spectrum very clean. Of course, it took much longer to get the anisotropy, and I'll spend most of the time on that. This time they got the full Nobel Prize divided by 2. That's the team, some of it with some replacements, some additions, Al Kogut's on the right, Ray Wise on the left. A few years later, he went back, got his prize for gravity waves. That's how it went. So when COBE was being built, this shows already the redesigned smaller doer. This had liquid helium in it that lasted about, 9 months to support FIRAS and Derby. The MR was passively cooled, observed for 4 years. That's how it looked, packaged for the rocket. This is the artist drawing on the left of what COBE was supposed to look like if it would have launched on shuttle. And what it in the end looked like is on the right. And that picture we remember very well, so I won't waste time on going on it. Maybe just that, of course, it flies over the Terminator, looks away to cold space. Sun is at 90 degrees, leading to all sorts of interesting problems with interpretation of possible spurious effects leading to anisotropy. This was the scanning, very effective low Earth orbit maneuvering to allow to get full sky coverage very effectively for anisotropy experiment, and so on. Also, I won't speak much about Derby. That was a long story. Took many years to contain difficult set of measurements. Even today, some in the room are trying to recompute that and see if something better can be squeezed out of the data. But that was their original press release picture of combination of 3 short wavelength and 3 long wavelength channels to indicate more of a stellar component versus dust component of the galaxy, and marvel that. But I'll mostly talk about the MR. So launched in '89, by the winter of '90, I would say atmosphere was pregnant with expectation. I was in Aspen meeting myself. This was just after, I think, AAS meeting when they make announcements or reports on what was going on. Some pictures like that, I retained the original slides. These were color print transparency, so I scanned them for this presentation. I remember distinctly how Mike Hauser, John Mather came to Aspen and amusingly reported how local newspapers talking about what was presented at AAS meeting used titles like "Satellites, Lack of Data Mystifies Astronomers." A little later, this was a UPI piece after the American Institute of Physics meeting where Dave Wilkinson was talking about COBE. So this is April 1990. I red-colored some of the quotes. Smoothnesses will still bring us a lot, and so on. If 1 or 2 years from now the pictures are still looking smooth, we'll be in trouble. So people worried whether what's emerging here is going to confirm Big Bang, as they said, and the linking of theory of structure formation to what CMB should have revealed to us. I didn't comment on it, obviously. I suppose everybody in the room knows this is on the left side, the picture, including the first 3 months of the measurement of mostly dipole anisotropy, and after it's removed, starts showing at the bottom at 30 gigahertz galactic emission. But of course, the big splash came in 1992. Discovery was announced. That was at the American Physics Society meeting in Washington. I had a pleasure to be there. Like a groupie, collected some dedications. My prized possession. That picture is still in my pile. And of course, it hit major news outlets everywhere. I flew to Paris 3 days after that meeting, and I've seen that picture on the screen in the plane shown. And what I wanted to revisit here was typically this picture from the discovery time was presented with the commentary that there aren't really real structures here. I mean, most of the stuff in this picture is noise because the instrument is really on the verge of being able to measure anything. So only statistical methods allow to make claims and formulations of categorical nature about what is the signal there, because you shouldn't think about any of those spots seriously. Well, so this is the same picture on the top, and at the bottom is Planck picture, reduced in resolution to the same roughly, and trying to replicate the color scale and everything. So obviously they don't look the same, but if you had a little bit of time to ponder that, I would suggest it's not all noise, and as we used to say working on COBE those days, that was pretty good for government work, all right? The full data set looked like this. 3 frequencies, 2 maps per frequency, possibility to combine them, subtract them, measure various effects. A lot of data analysis emerged in methodology, stimulated by COBE. It was a very different world before COBE maps were available with those few thousand elements on them. These are my old 2 slides from 30 years ago, where all of these spectral concepts and representation of data were being put together for my usage. This is returning to astrophysical noise, the picture that was repeated many times by many people, simply to recall that over frequency range where COBE looked 30 to 90 gigahertz, marked in green. For temperature anisotropies, it was staring at foreground emission minimum. And then in the spectral sense or analysis of the maps, so the first batch of papers actually had, well, Chuck led the paper on internal linear combination approach to combination of these maps in order to derive the microwave background anisotropy maps from them. It got a little bit more complicated later on. Some other methods emerged, all of that. In the power spectrum sense, it was interesting that it so happens that foregrounds as we knew them, and we used them in analysis of COBE data, which was Haslam map at 400 megahertz on the low frequency side, and the Derby map from, I guess, 240 microns as a dust tracer, as a template on the high frequency side. We corrected the DMR maps using those, and the power spectrum imprint of that in the convention of noise being flat is on the top. That's a 30-year-old plot showing that very steeply decreasing foreground template emission outside of the galactic cut. Pretty much made foregrounds for temperature, very fortunately for us, only touching the quadrupole itself, and in a very funny way, the galactic emission has a geometry that is sort of opposite to what we thought at the time is on the sky, and the quadrupole was diminished, as inferred from the data, by superposition with galactic emission. Then there was a little bit of a story of developing thread of power spectrum estimation. A big force on that was Ned Wright on the team. When I came to COBE, Ned already had a paper on 2-year data written. He's not a patient man. He pestered us a lot. Why haven't we, other people, done anything about it? We should publish it, publish it, publish it. We waited. I came in with my stuff, and it was an interesting quirk because with Ned's method of estimation, it appeared that that spectrum was extremely steep, very blue, and he insisted on it, and we had to sort this out, and eventually science team made us join horns or something. Ned was very gracious about it. His paper from 94 has a very bizarre abstract. We'll not go over this now because he quoted both his steep result and the correction that came out of this discussion. In 96, we settled the argument. My results were like this. So all these parameter plots, COBE was really sensitive to, in a nice way, to 2, just the slope of the spectrum and amplitude. Tremendously sensitive to amplitude. If you assume the slope close to Zeldovich, we got a 14 sigma measurement on amplitude. Very convincing in the end, but we couldn't really do physics on, say, 3 parameters, but that followed very rapidly when higher angular resolution data came in. So one of the recollection plots on eventually by 96, we estimated spectrum multiple by multiple. The top left plot is measurement from COBE maps with color bands of 95, 99, well, 68 bands around it. The best fitting spectrum, blue, slightly tilted, positive. But then when you reverse it and have data in black and models in color, it shows what at that time fitted a little worse than this pure weird spectrum. It was cold dark matter on large scales, but in the matter-dominated universe. Lambda was not yet the flavor of the day. The integrated Sachs-Wolf effect bends the spectrum upward a little bit at low multiples. It fitted data a little less well than the one without lambda, but not in a categorically discriminatable way. So we couldn't actually argue for lambda with COBE. But what we could argue against was what dominated 1980s. That was cold dark matter with a bias of about 2.5 on it, inferred from interpretation of correlations in galaxy distribution in the matter-dominated universe without lambda. Well, this had such a low prediction for signal that when COBE was flying and DMR was integrating, that was one of the contributors to, shall we say, pessimistic expectation of whether COBE would actually measure anything, because people thought that theory was compelling and predicted too little power for COBE to see. Well, it overshot by as much as you can see there.
Chris,
yeah.
5 minutes.
Yeah, I'm almost done. Doing all of this power spectrum analysis, map analysis, we could play with the data a little bit. This was my old plot presented at Morion in '96, where that should be considered the first glimpse, respectively, so of the last scattering surface as the MR revealed it to us. So on the left are 53 and 90 gigahertz maps on their own and their combination on top, and the difference at the bottom, roughly speaking, on scales above 10 degrees on the sky. I would say 3 to 1 significance of these structures. And again, like in the previous plot I showed you, one of the final amusement plots. Planck data on the right side, okay? So I'd say not so bad. Very, very, very nice indeed, actually, for what COBE was. And this was fun. What happened here? And stimulated tremendous impetus. Before COBE even was shut down in end of 95, data released in 96, proposals went in for what became eventually WMAP, Planck. People were thirsty for all the small-scale structure, baryon acoustic oscillations, cold dark matter, all of that. Predictions were amply available in a figurative, sort of cartoonish way. This was a stretch to cover quickly on the sky with CMB measurements what took us about 500 years on the surface of the Earth to get topography as we understand it right now. And that, of course, happened with WMAP, Planck, other experiments, and other people will talk about it. So I'll stop here and thank you.
Okay, so we're going to move. Jamie will come and start on Spherex. In the meantime, I'll take one question, one comment from the audience on if anybody wants to step up. Anybody? Okay, we'll come back. But now, time to have Jamie step in to tell us about a new project recently launched and perhaps some results. Jamie Bell.
Yeah, so I'd like to thank Joe for arranging this surprise. So Spherex is a recently launched cosmology satellite, just launched on the 11th of March of this year. It's not a cosmic microwave background satellite, but I will, in my time here, briefly describe the science and design and show you some early pictures as soon as that comes up.
You have it on there somewhere, yes. I don't know where.
Yeah, only this way.
No, I sent it. We sent it here. be under the discussion.
I am under this.
There it is.
This.
Book, yes.
Okay.
Okay, we're working on it. I think we're there.
Okay, thank you.
Okay.
Okay, so as I said, Spherex recently launched. It has 3 science goals. The first is to map out the abundance of water and other biogenic ices. This is an astrophysics goal. But then we have 2 cosmology goals. The first is a deep intensity map, which will be familiar to everyone here in the CMB. And the other is a cosmology map from a 3-dimensional mapping of large-scale structure to probe the physics of non-Gaussianity, probe the non-Gaussianity parameter. And in the process, Spherex makes an all-sky spectral survey, the first of its kind, where every pixel on the sky has a full spectrum, done 4 times. Okay, so I'll just briefly whiz through the science. So the first, as I mentioned, is to look at the abundance of water, and water in the interstellar medium, especially where stars and galaxies form, is not in the form of liquid or vapor. It's predominantly in the form of ice that's plated out on the surface of interstellar dust grains. And it's not just water, there's other materials, carbon dioxide, carbon monoxide, methanol, and so forth. And the way we do this measurement is to do absorption spectroscopy, where we look at a background star, and along its line of sight, there are these characteristic absorption fingerprints from these species that are out in the near infrared. And we can do this mapping over the early phases of star formation, from dense molecular clouds through to the time when stars are turning on. And the important thing here is that instead of doing this in dozens or hundreds of systems, we will have something like 10 million lines of sight with high signal-to-noise measurements of these ice species. And I can tell you from our initial data, we see ices in abundance in the interstellar medium. Our second theme is what's called intensity mapping. And the idea is if you want to study the evolution of galaxies, you can study the individual objects, or you can look at the total background light that they produce. And we're doing this in an anisotropy type of measurement, using the fact that galaxies trace out the distribution of dark matter. So here's a simulation, and if you studied these galaxies with a large telescope, you'd pick off the bright ones, and your data set would look like these dots, which are interesting, but all the information, all the emission from all the galaxies is actually in the map. And so one can map out this structure, which has been done by missions like Planck and Spitzer and so forth, and Herschel. But the key is really spectroscopy, to break those maps into multiple colors. And so with Spherex, we have 102 bands, and we can make intensity maps in all those bands. And this mapping is very powerful because you're seeing the emission from everything, all the galaxies, dwarf galaxies, it doesn't matter. It's basically tracing total luminosity, as well as anything else that might correlate with, feel the force of gravity from dark matter. So it's very orthogonal and very powerful method, and very exciting for our CMB because we can apply many of the lessons we've learned in the microwave background to produce maps with completely different detectors in a 3-dimensional way. And then our third theme is how did the universe begin? And basically here what we're doing is we're looking at the 3-dimensional picture of galaxies to probe the amplitude of non-Gaussianity. Of course, with the microwave background, we've basically hit cosmological limits on non-Gaussianity. So this 3-dimensional map that we get with galaxies contains significantly more cosmological information, and therefore we can do a factor of 10 better than the cosmic limits we get with, close to cosmic limits we have with Planck. So this isn't an easy job, but in one slide I can kind of describe how it works. So here's a cartoon of the distribution of matter, microwave backgrounds out at the edge of this map. And so this kind of shows, again, in a cartoon fashion, the redshift and photometric redshift coverage of Euclid and its relative sky fraction. Roman, now of course this is evolving. This is the weak lensing survey. There are other surveys being proposed and studied. But with Spherex, what we're doing is we're mapping the whole sky with spectroscopy. So we get 4 pi steradians, and we get a continuous redshift coverage. The most accurate redshifts are coming at low redshift, just basically due to the source brightness, and that peters out as we go to higher redshifts, redshifts 2 and 3. At these low redshifts, we basically have a cosmic variance limited survey. And so the combination of this continuous redshift coverage and all sky coverage allow us to constrain non-Gaussianity through the power spectrum and the bispectrum. It won't be easy. And so our target is to push this FNL parameter down below 1, about a factor of 10 improvement. Okay, so that's the science in whirlwind fashion. This is the instrument. So the first thing about Spherex is this very unique design with these cones that you see, and that's to radiatively cool the instrument in low Earth orbit. And the cones here allow heat to bounce out to space. The telescope and detectors also radiate, so there's really 5 stages of cooling. And that cools the telescope below 80 Kelvin and the long wavelength detectors below 55 Kelvin. Spherex has a small telescope, but a very wide field of view. Cover 40 square degrees at a shot with 6 arcsecond pixels. It's an off-axis, wide field, low side lobe telescope design, where the beam splits into 2 bands, a short band and a long band. There's 24 million pixels in the focal plane split between 2 focal planes. And then the way we do spectroscopy is simple, but a little puzzling sometimes. Basically what we do is we just put an interference filter on top of the detectors, and the interference filter, the wavelength changes as you go along the focal plane, and that's it. So to take an observation of a source, we need multiple pointings, which we allow the spacecraft to do. And so the spacecraft has to be agile and point stably, but that's standard stuff these days. Okay, so here it is all put together. So what you see here is Spherex on the top. There's actually 4 satellites below us on this gold ESPA ring. These are a heliophysics experiment called PUNCH. There's actually 4 satellites there. This is then the adapter ring that goes to the vehicle. And then surrounding us is the fairing, is enormous fairing of a Falcon 9 rocket. We're barely filling half of it here. Really, really impressive. Okay, and then here's the launch. I'm afraid it's without sound. It's better with sound. So this was on, oh, here we go, great. March 11th.
Spherex and Punch on their way to map out our universe like never before and revolutionize space weather forecasting.
Stage separation confirmed.
And back ignition.
Stage 1 boost back startup.
Coming up next, we will see fairing deploy, and that's when the 2 fairing halves will separate and expose Spherex and Punch to the atmosphere of space.
Fairing separation confirmed.
In about 30 seconds, we will have payload deploy of Spherex.
Spherex separation confirmed.
Spherex is drifting away from Falcon 9's second stage, confirming deployment. The mission isn't over yet. Falcon 9's second stage is still carrying NASA's Punch mission.
Separation confirmed.
Wow, look at that. To actually see them, that's great.
Yeah, okay, so the launch was very successful. We got into exactly the orbit we wanted. This shows the cool down happening. So at the beginning here, when we initially cool down, the spacecraft is being degassed by having the Earth warm up the instrument. That's these oscillations you see. When we finally eject the lid successfully and let things cool down, the detectors get down to 45 degrees Kelvin in low Earth orbit, and the telescope to 62, regulated to 10 microkelvin. Here's some just first light images. So you can see here the six bands. Wavelengths vary over the filters, which is shown in color to give you some idea. This is a movie, so you also can just see the data's coming through. Each of these exposures is really 2 minutes. This band, by the way, is the helium emission line from our atmosphere. So in that band, we knew about that, but we suffer some photon noise in that band. And then obviously these are stars. The center of them are saturated as expected. And the full moon here is shown for scale. So you can just see the enormous field of view and data gathering that is taking place. We've now measured our point spread function, our sensitivity in flight, and it's basically looking as expected. Here you can see the pre-flight predictions in blue and the measured performance in the green lines. This is in AB magnitude, so higher sensitivity is up, and we're doing a little worse in band 4, but better in bands 5, 6, 3, and within the range in bands 1 and 2. But all in all, we're quite happy with the sensitivity. We've started taking science observations. That started on May 1st, after our checkout period. And so generally speaking, we're observing 90 degrees from the sun, so we're tracing out a great circle. Each of those observations is, of course, pointed. This shows the coverage pattern in 13 days of observations. You can see here, these are the ecliptic poles. And so at the ecliptic poles, we have 50 times, roughly speaking, 50 times the depth that we have in the all sky. And it takes a couple weeks to really get complete wavelength coverage anywhere. So in these yellow bands, we're now starting to get the complete wavelength coverage. On June 21st, the data will start to become publicly available. And basically, in calibrated image form, this data rolls off the conveyor belt, and you can look it up at the IPAC URSA site. Just to give you some visual representations of first light images, what you see here is an image of the galactic plane taken in 2 bands at the same time. And these are spectral images, so the wavelength is varying along the image. And so in the short band here, this is the same region. You see lots of diffuse scattered starlight and opacity from clouds in the galactic plane. And then here at the long wavelengths, you're starting to see through the dust in the galactic plane, which is nice to see. I mean, we expect that, but it's pretty cool. You'll notice some opacity here. We see water in these clouds just by watching the spectra change as we sweep through it. This feature is bracket alpha line emission from hydrogen. And then finally, this is a series of images made in the N11 region of the Large Magellanic Cloud. And it was observed also in 2 bands here. And so first the short bands, here you can see this nebula, and then here in the long bands. And you can see features lighting up at particular wavelengths. In particular here, at the longer wavelengths, you'll note the strong emission from PAHs at 3.3 microns. So we've made some mosaics. So these are single wavelength images. And so you can see this nebular region, again, at these multiple wavelengths. And here, as we go over it at short wavelengths, as this movie loops, you can see these regions light up, and that's the ionized sulfur line. And here, when we hit 3.3 microns, you'll see very prominent PAH emission, which we see ubiquitously over the sky. So it's very exciting times here for Spherex, and I'd be happy to talk about it at coffee if you have any questions. And thanks for listening.
Yeah. So thanks so much, Jamie, for this last-minute presentation. I think we've had something old, something new in this session. I think we'll go for coffee now, and then That'll give us time to have a full discussion at the end of the next session, which will be related to some of what we heard about already. So coffee is ready, I believe.